All right, hey Parrot, sorry I can't be there today. My son is sick right now, so he's been up, he's been having a fever. My wife's with him right now. Hopefully, I'll be in on Wednesday for your quiz, so don't forget you have an upcoming quiz on Wednesday. In order to study for that quiz, please go through multiple times quick quizzes 7 through 8. Quick quiz 7, it's the simplest of the 10 quizzes. All you have to do is look at a element, and you have to realize that all elements in the same group or family, in other words, all elements in the same column, have very similar properties. So if they're in the same column, they're going to be most similar. Quick quiz number 8 is metals versus nonmetals, alkali metals, alkaline earth metals, nonmetals, metalloids. You need to know where the positions of all of those are on the periodic table. And don't forget, for these ones, it's open note, so please go ahead and refer to your notes. But know that on Wednesday's quiz, you're only going to be given the blue laminated periodic table, and so you're going to have to know the terms. You're going to have to know where those things are on your own. Quick quiz 9, predicting periodicity. Predicting periodicity is the same exact stuff that we did in class on Monday. So you're going to be given a list of properties of different elements, and you're going to have to figure out, are they in the same row, are they in the same column, and if they are they in between two values, or are they greater than a value or less than a value? Quick quiz number 10 is going to go over the things that we're going to be talking about today, which is using the periodic table to figure out how many valence electrons each element will have. Okay, and you can find extra information on the valence electrons if you go to the Part 2 folder and then go to X, which is Roman numeral 10, valence electrons in the Bohr model, and in there is a reading underneath text and homework. There's a reading that I'm going to assign for tonight, which is called Bohr model, electron shells, and valence. And then you also have the Bohr model and valence electrons homework. Please do that. All of this stuff will be on the test. Okay, so take out your Notability, and please follow along a little bit as we go through this. So, as a quick review, you have the history of the atom. So remember the first couple guys who came up with the idea of the atom. You have Democritus and Aristotle. Okay, Democritus and Aristotle, they thought of what is stuff made of. Okay, and so they philosophically were like, what is everything on the planet? What is it made of? And Aristotle, remember, thought it was made of elements: earth, water, wind, and fire. If you watch Avatar: The Last Airbender, that's your guy. And Democritus thought atomos, which means unbreakable. And so those atomos are those unbreakable particles. All right, then it wasn't until another couple thousand years that you had Dalton. Okay, and Dalton did experiments on matter. That's the big thing. He did experiments about matter. He thought that atoms were unbreakable. And he thought they could combine to make molecules. Okay, and so if he was to visualize an atom, he probably would draw something like this: a little circle, a little three-dimensional sphere, a little marble. Okay, a little unbreakable three-dimensional sphere. Okay, once you get past Dalton, you have Thomson, and Thomson came up with the plum pudding model. All right, and J.J. Thomson he discovered the electron. So J.J. Thomson's idea of the atom, if you remember, was this matrix of negative charge. You had this negative charge all over, and then you had these positive charges spread throughout. So you have these negative charges spread throughout, and then you had a positive matrix. Sorry, messed up. You had a positive matrix, and then you had the negative charges floating around in it, just like plum pudding. So you had negative charges floating around a positive matrix. Well, then you had Rutherford. And remember, Rutherford did that gold foil experiment. And Rutherford said that, hey, you know what? There is actually those positive things. It's not just like a field. That positive thing is the small positive nucleus that's in the center. And that means that most of the atom is empty space. There's nothing really out here, but then you do have these random negative charges that are just kind of floating around on the outside. And that was Rutherford. Okay, well then, a couple decades after Rutherford did his experiments, a guy named Bohr, Niels Bohr, really interesting fellow, he came up with what is called the planetary model. Okay, and this is the one that you're probably most familiar with when you think of a picture of an atom in textbooks and stuff. So Bohr, he said that, okay, you have the neutrons and the protons in the center, okay, but then you have the electrons in these nice, predictable orbits. Around the outside. So these electrons are in these nice, predictable orbits. So going through everything, Democritus thought atom was just an unbreakable element. J.J. Thomson came along. He said, okay, there's these negative particles, these negative electrons. Since there's negatives and not everything is electric, it must have a positive charge somewhere, so that positive charge is just distributed everywhere. Then you get Rutherford with the gold foil experiment. Rutherford said, okay, you have a positive nucleus right there, right in the middle, and then all these electrons floating around it. And then Bohr put those electrons in these nicely, clearly defined orbitals. Okay, so this is the model that we're going to work off today when we talk about valence electrons. All right, so valence electrons. Okay, valence electrons, all they are electrons in the outermost orbit of an atom. Okay, valence electrons are the electrons that react. Okay, so these are what determine the reactivity of every element, these valence electrons. There's a couple of ways that you can figure out the valence electrons, and the simplest way is just simply when you see a periodic table and you see those families, okay, if you ignore the transition metals, we're going to ignore those transition metals. Nobody likes them anyway. You can easily determine how many valence electrons there are by looking at the column that it's in. And above each column, you'll typically see a Roman numeral. So everything in the first column here, so your hydrogen, your lithium, your sodium, okay, they all have this many valence electrons. So they have one valence electron. Okay. The second column, 2, okay, has 2 valence electrons. Okay. Now what you're going to do is you're going to skip these transition metals. The valence electrons there are kind of weird. The outermost aren't really the outermost. It's really complicated. So we're not going to have you, as a sophomore, junior level chemistry, we're not going to have you memorize these just yet or understand how those work just yet. So we're going to skip all the transition metals and we come over here to row number 3. Those have 3 valence electrons. You have row number 4, which has 4 valence electrons, and 5 valence electrons. You have 6 valence electrons, and then, sorry, I'm making this table a little bit icky. So you have 6, and then you have 7, and then all the way in the noble gases, you have 8 valence electrons, with one exception. And that one exception is helium up here. Helium, even though it's in the noble gas column, even though it should have 8 valence electrons, helium only has 2 valence electrons. It only has 2 electrons anyway, and we'll talk about that in a second. All right, so these orbits and these valence electrons, when you draw them, you're only typically drawing the outermost shell, but they always fill up like this. So it's kind of like peeling back an onion. You have your nucleus, and then you have your first orbital, Okay, you have your nucleus, and then you have your first orbital. This first orbital is so close to the nucleus that you can only fit 2 electrons around it. And sometimes, by the way, sometimes these orbitals are also called shells. And this also, how many shells an electron have, is also the period that it's in. So period number 1 has 1 shell. Period number 2 has 2 shells. Period number 3 has 3 shells. Period number 4 has 4 shells. 5 is 5. 6 is 6. And 7 is 7. So that's how many shells you have on the outermost layer. So the first one is so close to the nucleus that it can only accommodate these 2 hydrogen and helium electrons. The next orbital, okay, can handle 1, 2, 3, 4, 5, 6, 7, 8. So you can handle up to 8 valence electrons. And the third column can handle up to, third period can handle up to 8, fourth period can handle up to 8, and so on and so forth. All right, now here is a rule that you always need to follow, is that atoms always want a full shell or orbital. Okay? And for most orbitals, this means 8 electrons, unless the first period, unless you're in the first period, in which case you want 2 electrons. Okay, 8 electrons, unless you're in the first period, you want 2 electrons. This is known as the octet rule. Octet means 8, the rule means 8. All atoms want a full shell of orbital. That makes them stable. Okay, so all of the noble gases, the reason why they don't react with anything, or it's really hard to make them react, is because they either have 2 electrons in the case of helium, and then all of the other noble gases, they have 8 electrons. So they're not going to react anymore. But if they don't have a full orbital, they're going to keep reacting until they get more of those electrons, or until they lose them. Because if you only have 1 valence electron, it's much easier. If you only have 1 valence electron, it's much easier to lose that 1 valence electron and get to 8 or 2 than it is to gain 7. So atoms are lazy just like everybody else, and they want to either lose the minimum amount or gain the minimum amount. When we talk about ions next week, that's going to be important, but just keep that in the back of your head for right now. All right, so I just wanted to point something out to you guys. If you go back to Schoology, right, underneath the labs and activities and extras, there are these charts here. Okay, and you can open up these charts on a home computer, or you can open them up on your iPad at home. That's fine. Okay, so what I'm downloading now is just the valence electrons, the energies of all these valence electrons. So ionization energy is how much energy it takes to pull an electron away. So the nucleus is positive, right? And the electrons are negative, and they're going to be held together kind of like a magnet. The closer to the magnet that the electron is, the harder it is to pull away. Okay, and also the closer it is to having a full octet, the harder it's going to be to pull away. So what this is showing is right here with hydrogen, and let me zoom in a little bit so you can see it a little bit better. Okay, so what it's showing here is with hydrogen, okay, the first ionization energy here is 1,312. So we have ionization energy of 1,312. There's only 1 electron. So it takes a lot of energy to get it off. Now we get to helium. Helium is stable, so notice the ionization energy here jumps quite a bit. It doesn't really want to lose any electrons. It has 2 valence electrons. It's pretty stable. All right, now we go to lithium. Lithium has the full inner shell, and then you have this big drop in energy. So the first ionization energy, the first amount of energy to get rid of that first electron is 520. Remember, the valence electrons are always going to have the least amount of energy to get off because they're furthest away. They're furthest away from the nucleus. So this one, these 2 are in the first shell. They're happy. It's hard to get those off. One is 7,000. The other one's 11,000 joules of energy. Whereas this electron here, it's only 520. All right, we go to beryllium, which has 4 total electrons, and now you're beginning able to see these shells, right? Here's the inner orbital, which takes a whole lot of energy to pull off, and then you have your 2 outermost valence electrons, which take much less energy to get off. So here is the outer shell, and here's the inner shell. Okay, now we keep adding electrons. We go to boron. Boron has 1, 2, 3 valence electrons, and then there's a big jump right here. Big jump for the inner shell. Okay, you get to carbon. Carbon has 1, 2, 3, 4 electrons in that second shell, and then the first shell you jump over to electron number 1, electron number 2. Now we get to nitrogen. Nitrogen, it's even easier to get that first electron off. You have 1, 2, 3, 4, 5 valence electrons, and then you have that innermost shell up here. Okay, moving to oxygen. Oxygen has 1, 2, 3, 4, 5, 6 electrons, and then way up here is the inner shell. Now, one thing that students always get wrong is they want to see these ones, they see these electrons farther away from these electrons, and they say, oh, these ones are farther away, they must be easier to pull off. No, remember, this is energy. This is how closely tight or how powerfully held these electrons are. So these electrons are right up against the nucleus. These don't want to come off. This one down here is the one that's going to come off right away, followed by this one, followed by this one, followed by this one, followed by this one, followed by this one. Okay, these ones take a whole lot of energy. You're going to really pump that thing full of energy and get those ones off. Okay, going to fluorine. Fluorine, once again, outermost electron, easiest to pull off. A little bit harder, a little bit harder, even harder, even harder, even harder, even harder. And then these guys you're not getting off. So now we're in fluorine. Now we're almost to the second noble gas. Okay. Neon. Notice neon, you have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, and then a big jump to that inner shell, that first orbital, 1, 2. Okay, now we're going to the third row of the periodic table. Now notice, look, watch this. Okay, so here, it's hard to see on this scale. Let's see if I can pull it back a little bit. Nope, it's not working. All right, but notice on the chart here, you have one electron that has an energy of about 500, and then it jumps 5-fold. So there's actually one valence electron here, and then you have 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2. This one is a lot different than the other ones. It's a little bit easier to see once we add a couple more. Notice there is a little bit of a gap in between here. 2 valence electrons, 1, 2, 3 valence electrons, all beneath, so it goes 500, 1800, 2700. And then there's a big gap here. This is a logarithmic scale, so it's a little bit hard to see the difference between these, but you can see now you're beginning to see the trends. 1, 2, 3, 4 valence electrons, and this one is for silicon, and then you have the 8 here, and then the 2 here of the innermost shell. And you keep going up. 1, 2, 3, 4, 5, and then you have your second orbit and your third orbit. Over here you have 6, second orbit, third orbit. Here you have 7, middle orbit, innermost orbit. And then you have 8, middle orbit, innermost orbit. And then you go to potassium, and you're going to start adding another row of these going here. You can only really see it in the chart where you have 400, then 3,000, then 4,000, and so on and so forth. So go ahead and look through these a little bit and see if you can figure out where the valence electrons are based on the numbers given to you and based on the charts. Remember, the valence electrons are going to be the easiest electrons to pull out. There's going to be a big gap between the outer orbital and the inner orbitals.